Good afternoon, everyone. My name is Robert Smith from Plextek RFI, and today I'm going to be talking about a cost-effective hybrid input-matched GaN transistor for S-Band radar applications. So I'm going to start off by describing the transistor itself that we designed. This was targeted at a frequency range of 2.7 to 3.5 gigahertz. I'll talk about the motivation behind the design itself, and some local measurements that were taken on the transistor. We subsequently used this transistor to design a single-stage S-band power amplifier between 2.7 and 3.1 gigahertz. So the use of gallium nitride on silicon carbide is now widespread. It's moved from a research area into being commonly used in industry for applications in high volumes. And the cost per watt has now decreased to that below gallium arsenide. So this is according to our colleagues at Qorvo. Now, because of the power density that you get out of gallium nitride compared to gallium arsenide, the cost per watt has now decreased. And although it's still more expensive for the area compared to gallium arsenide, the relevance of this I'll get onto in a minute, it also has significant technical advantages for power amplifiers. So the main one is the increased voltage that you can run the transistors at. This has a few benefits, one of which is that you're matching to a higher output impedance, and the benefit of that is generally you can realise broader band designs. Another advantage of the higher drain voltage is that you have lower drain current, so your I2R losses are reduced. Also, silicon carbide is a better thermal conductor compared to gallium arsenide, so it's easier to get the heat out of the device, and you can run the channel temperature of a gallium nitride FET higher than you can for a gallium arsenide FET. So in an active phased array radar, any cost savings you can make can add up quickly. You might have hundreds or even thousands of power amplifiers in one phased array radar. So if you can save a little bit of money on one of these amplifiers, that will quickly multiply up. The space on a PCB is also a key consideration. So in an active phased array radar, the elements tend to be spaced about half a wavelength apart from each other. And so the space that you then have to implement your transmitter channel is limited, is physically limited by the frequency that you're operating at. So you don't have unlimited space, you have to fit your devices into the given space. So what I'm outlining here, this is a typical GaN MMIC. This is actually one that we designed a couple of years ago on UMS's process. This is for X-band applications. But the reason for showing this is really to look at where the space is being used on a gallium nitride MMIC. So we can see that actually most of the space is not used in the active transistor, which is where GaN really has its strengths, but instead is used for passive matching, and it takes up most of the die area. Now, although the cost of GaN is decreased, as I explained, if we can decrease it even further, that's obviously good for end users. So one way we might be able to reduce the cost would be to implement this matching not on gallium nitride, but on a cheaper process. And if you wanted to implement gallium nitride PA, there are a few different ways you could do that. So the GaN MMIC, which I've just described, this is a discrete gallium nitride transistor. So in the middle we've got just a GaN power bar that's in a low-cost plastic package. And all the matching is done externally, so we've just got some SMT components on the input and output. Alternatively, we've got a hybrid input-matched gallium nitride transistor, and this is what I'll be describing today. If we compare these three approaches, starting off with the gallium nitride MMIC, it's got a few advantages. So we've designed loads of these at Plextek RFI, and they work great. We like MMICs for a lot of different applications. The input and output is internally matched to 50 ohms. So this means that it requires the lowest customer effort because they can put this onto their board and integrate it into their system. It also takes up the least amount of space because you don't need any external matching components. It's all done on the die. It also tends to give the best performance. Disadvantages is that it tends to be the most expensive because you need all of that space on your GaN wafer to implement the passive matching. And it's also not tunable. So as you buy it and implement it into your system, you don't get a choice between matching for optimum output power or for optimum efficiency. But it does take up a very small amount of space on your PCB. If you go the other way to the discrete GaN solution, This is an unmatched transistor in a low-cost plastic package, and the cost of the device itself will be the lowest. Now, you will have the additional expenses for the SMT components, but for the purposes of this, I'm assuming that they're negligible compared to the cost of the transistor itself. You still get good performance out of this, and it's completely tunable. You can choose the frequency that it works at, up to a point, and you can choose whether you want to match for output power or efficiency. But it requires the highest level of customer design effort and also the largest space on the PCB. Now, manufacturers can try and mitigate this by providing reference designs, and we've designed a few of these for Qorvo. But if you wanted to use a different PCB substrate, you'd need to change your matching. So there's still design effort required for the end user. A sort of compromise between the two is the hybrid input match gallium nitride transistor. So we internally match that to 50 ohms at the input, but leave the output unmatched, so that we match that on the PCB. This is a lower cost solution compared to the gallium nitride MMIC, but slightly more expensive than a discrete GaN transistor. You can tune the output for the performance that you want to get. It takes up more space than a MMIC, but less than a discrete GaN solution, and it requires a certain amount of customer effort depending on how you want to implement your output match. So for the QPD1020, which is the product that we designed in conjunction with Qorvo, we went for this hybrid input matching approach. Now, I can't show you the picture of the die itself, but this is basically how it's laid out inside the package. So we've got a 6mm by 5mm QFN plastic package. We've got our GaN die here in grey, and you can see that this is small, so we're not using a huge amount of space on our gallium nitride wafer, which is helping to keep the cost down. And we're using a passive gallium arsenide input matching network. So this is a different Qorvo process. It's low cost, it has no active components on it, so all we can implement is resistors, transmission lines, capacitors, inductors. That's fine, because that's what we need for our input matching network. And the cost is significantly lower compared to either doing it in active gas or in gallium nitride. Now, we chose this package because it's a proven package that's used in existing Qorvo products, and that reduced the design risk and improved the speed of development. So you can see that we've tried to increase the dimensions in the X of the passive gas network as much as possible, and that was to reduce the bond wire inductances. So we could actually have put this into a smaller package and maybe cut the size down a bit, but we decided that to speed up the development and reduce the risk and use an existing package. So the approach we took to the design was to first pick the package and see what space we had available, and to work out how our two die were going to be bonded in there and what space we'd have available. And like I say, we made the X dimension of our passive gas network as big as possible. We looked at the output impedance that we need for our device. Now actually, with this design, we're almost designing it in reverse, because for a conventional power amplifier design, you design your output first and then you design your input. Here, what we've had to do is design the input first based on what we think the output's going to look like, and then we design the output at a later stage when we've got the parts back and we've done load-pull measurements on them. So we estimate the bond wire inductances and the package source inductance, and we then design our input matching network to do two purposes. One is to stabilise the device in band, and the second is to give a good input match across our frequency band of interest. We start off designing using PDK process design kit elements that are provided by Qorvo, and we optimise the schematic design to give the performance that we want. Then we use that to generate a layout, and we EM simulate it, and we re-optimise as a result of the EM simulation. Now, because we're using a plastic overmoulded package, that plastic has an effect on the performance of the die that isn't modelled by the PDK, and the usual effect is that it brings the performance down in frequency. So when we do the EM simulations, we find we then have to do a bit of retuning to shift back up into the intended band. So we manufactured the transistor and got some measured S parameters off it. So this is just the transistor itself with no output match, measured with S parameters just into a 50 ohm environment. You can see that we're getting a good input match here across our 2.7 to 3.5 gigahertz band. we're getting about 10 dBs across the band, getting as good as 20 dB in the middle of the band. And you can see that we've got the classic two-pole low-pass response. In terms of the gain, we're getting about 13 dBs of gain, and this is pretty good considering we haven't actually matched the output yet. We're just terminating that into 50 ohms. And the SG2, as we'd expect, it's highly reflective because we haven't done any matching on the output. We're just looking into the output impedance of the transistor itself. So then Qorvo also did some load pull on this transistor, and what we can see is that we've got a number of different contours in different colours. So the power contours are in red, the PAE contours are in pink, and then the optimum gain contours are in blue. And you can see these three black dots here show us the optimum impedance for each scenario. Now, this shows that actually we need to pick the right impedance depending on what we want to be doing with our transistor. If we want to go for maximum power, we'd match it here. If we wanted to go for maximum PAE, we'd match it here. And if we went for compromise, we'd want somewhere in between. So I've just shown this data here for 3.1 gigahertz, but it was also done at 2.7 and 3.5 gigahertz. And here's a summary of the data. So if we choose to match for output power, you can see that across the band we can achieve something like 45 dBm. That's if we go for optimum power rather than optimum PAE. That would give us a resulting PAE value of roughly about 55%, so it's still pretty good. But if we wanted to tune specifically for PAE, then we see we could do better than that. We could do 10 percentage points better if we choose to match for PAE. But the disadvantage is that the power decreases, so we're now going down from 45 dBm to about 44 dBm, something like that. So there's an advantage to being able to use the tunability, because one customer may want to go for power and the other might want to go for PAE. So we took this local data and these measured S parameters, and we used the transistor that we'd made to implement a power amplifier. And this was designed for 2.7 to 3.1 gigahertz operation. Now the module itself is matched for 2.7 to 3.5 gigahertz, but the power amplifier was designed for a smaller band, and that's generally because in S-band radar applications you don't need to use the entirety of the. If we use only half the band, which is common for radar applications, then we can really optimise for that band. And what we do is we first ensure that the PA is unconditionally stable in band. That's our first task. We then include the gate and drain biasing networks, and we try to make sure that they have as little impact in band as possible. We then design our low-loss output matching network to give the impedances that we want, and what we chose for this was to optimise for power added efficiency rather than for output power. And we add gate and drain networks to give us some low-frequency stability. This is especially important for GaN because you find that at low frequencies, gallium nitride has a lot of gain, and you can run into potential stability problems. So you have to pay a lot of attention making sure that your stability is fine down at low frequencies. We optimise our schematic design, we turn that into a layout, and we do EM simulations and any optimizations that are necessary for that EM. And this is a schematic of the PA. So you can see we've got the device here in the middle. We've got DC blocks on the output and the input, and we've got a small amount of matching on the output because we haven't done any matching internally. We've got a tiny bit of matching on the input, and these are all our low frequency stability networks, so that we've decoupled really down as far down to DC as we can. And it's worth noting actually that these networks would be required even if you used a MMIC or a discrete GaN solution. So there's nothing inherently necessary about this particular design that needs them. You wouldn't be able to put high enough capacitance on your MMIC to negate the need for these. Then we've got a picture of the PA itself, so we can see the device here in the middle. We've got a little bit of matching on the output. We've got our low frequency decoupling on our gate and drain. And you can see here there's very few components needed on the input, and this is a really nice compact design. So the PCB dimensions itself is only 40 millimeters in the x direction. But you can see here that actually a lot of that is 50 ohm line, and the only reason for that is basically so that we could fit these banana sockets on for ease of testing. If we didn't put these on, you could see how we could cut down the size of the design even smaller. And this is a nice compact design that would be useful for a radar application. As with other evaluation boards we've done for Qorvo, we've also put a hole in here which goes underneath the device so we can use that to monitor the temperature while testing, and that can give customers an idea of the long-term reliability of the part. So I'm going to show you some results now for the overall PA. It's worth noting that when we show the results, we take into account these SMA connectors and all of the PCB losses, so we're not de-embedding anything. This is the actual performance that we measured de-embedded to this plane here. And the measured PA results, you can see we get a good input match across the band of interest, greater than 10 dB. We've increased our gain by adding an output match, as we'd expect, and now we're getting about 16, 17 dBs of gain across the band, and actually we're getting gain a little bit higher than we designed for as well, so it's quite a broadband design. And you can see our S22 is also improved. Now it's still fairly poor, but we normally would expect this with a power amplifier because we're not matching for conjugate, we're matching for PAE in this case. So we also designed, I've shown the results here at 25 degrees C, but we also designed it to work down to -14 up to 85. So that means we need to pay more attention to the stability of the design to make sure it can work over the wide range of temperatures. We measured about 5 of these devices and we found the repeatability was very good, so I've just shown you a typical device here. And in terms of the large signal performance, we measured 10% duty cycle and 128 microsecond pulse width, so a typical sort of radar pulse width, and measured the output power at 3 dB compression. And we can see that at the high end of the band it's giving a minimum of 20 watts of output power, rising to 25 at the low end of the frequency band. And we're getting a drain efficiency of around about 57% at room temperature, dropping to maybe 56% at the high end of the band. But it's a nice flat response. There's no hint of roll off here, and we can see that we managed to hit the design band that we were aiming for. So just to summarise, I've discussed the hybrid approach of using a GaN power bar and a passive gas input matching network, which reduces the cost compared to a MMIC and also requires, it allows you more flexibility at the output compared to using a MMIC. It's easier to integrate than a discrete GaN solution, so you need far fewer components at the input compared to using a discrete GaN die. We've designed a transistor based on this approach using a cost-effective proven plastic overmolded package, and that gives us a good input match at the band of interest, and that gives us a good transistor to build a power amplifier with. So we then went and built a power amplifier based on this, and we designed it for high efficiency operation with 20 watts minimum of output power and 55% efficiency. It was a compact layout with minimal off-chip components. And if you want to find out more about this product, there's more details available on the Qorvo website, including a data sheet, and we're also going to have an article coming out on this in RF Global Net in the near future. Thanks for your attention.